All right, we're back. Here's a little example of the one-sided Z transform. And it's actually a pretty good example of Z transform in general as well. It's a little more involved than the ones we've been doing, so please give it some attention. Here's a one-sided Z transform that we came up with on the previous little video for this simple difference equation. And now we're going to say let's find the output y of n, given that the input is a cosine that's causal, so it's got u of n multiplied by it. And we're going to give some values. A is 0.9, B is 1, and an initial condition is given as 3. Okay, so let's see how we would solve it. So we have to actually solve this thing. How do we solve it? Well, the first thing we do is we have to find out what x of z is, right? X of z is the z transform of this cosine. Well, the one-sided z transform and the two-sided z transforms are the same for this thing because this thing begins at 0. So the one and the two-sided z transforms are identical. Looking in the tables in the book, so make sure you can use the tables in the book. This is directly out of the table for the z transform of a cosine. Plugging in cosine pi over 5, we just get numbers. So there's x of z, and I should put, I suppose, x plus here because it's the same as x of z. All right, what is y of z? Y of z is this part, which is that part, where I've plugged in a is 0.9, the initial condition is 3, and then we've got this part, which I've written out down here. Well, this part over here is easy. I say it's easy. We've done this before. This is just a decaying exponential. So let's focus on the inverse z transform of this thing, which is a little more complicated. Okay, so that's what we're going to do a little bit of time on. All right. Well, first of all, we got to turn this thing into a ratio of polynomial so that I can do partial fraction expansion the way we're used to. And I use convolution, MATLAB convolution. I'm going to show some MATLAB here in a second to find the product of those two polynomials. Okay, so there's the whole thing. I'm kind of wanting to do this using MATLAB instead of the by hand approach. All right, through the magic of computers, I've gone ahead and brought in a MATLAB window, and I just wanted to show how I would find this polynomial here. Here's my little MATLAB window, and this thing that I've outlined in blue here, you can kind of see it. It's going to be, I'm calling it A. Let me get that blue out of there. I'm using convolution. I'm convolving the first polynomial, which has coefficients 1 and minus 0.9, and the second polynomial, which has coefficients 1, minus 1.62, and 1. And then let me move that out of the view here and show the result. There I've already typed in this is the command window, so I've typed in that command, and those are the results. So those are the coefficients for the denominator polynomial. All right, so there's the term number 2 that I want to find the inverse z transform of. All right, now I want to do partial fraction expansion of this term. And it's going to, if I write it out, always write this out, please. If this whole thing is going to result in 3 different terms in the expansion. It's going to have one term that has this denominator and 2 more terms, because this is a second order denominator. So I'm going to have 2 more terms, and it's going to turn out that these poles and residues are complex. All right, so to save us the trouble of figuring out the partial fraction expansion, I'm going to use the following MATLAB commands. Okay, I'm going to tell it what the numerator coefficients are, 1 minus 0.1 and minus 0.81. The denominator coefficients, those are the coefficients of the denominator. And I'm going to use the residue z command, where I give it the numerator and the denominator, and it's going to give me the residues, the poles, and c, if you remember from last time, it represents any values in case this is not a proper fraction. But this is a proper fraction, so we're not going to get anything for c. And so residue z is going to tell me what to put there and there. All right, here I've kind of jotted in with my bad penmanship how we're going to get the first residue. I only need the first one because the second one is going to be the complex conjugate. The third one is going to be this guy, and so I've already kind of given you the result. But I need the magnitude and the phase of the residues. I need the magnitude and the phase of the poles. If you remember, we're going to plug those in to this equation, which is going to give us this in a nice decaying exponential sinusoidal form. All right, let me bring up MATLAB, and I'll show you in much better penmanship how to run that residue z program. So here I plug it in, and let me just go ahead and run it. I'm going to hit that, and then if you hit F9 key, which I'm going to do, it actually runs that command. This is in the editor window. And so I'm going to pull over, and you see what happened is it brought this command up in the command window, and then since I didn't have a semicolon there, it lists out the answers. Those are the residues. You see the first two are complex conjugates of each other. The third one is a real residue, 0.23. The corresponding poles, there's the pole corresponding to that residue, there's the pole corresponding to that residue, and there's the pole corresponding to that residue. So what I need is, I only need the magnitude and phase of this first residue, and it corresponds to this pole, so I need the magnitude and phase of this pole. Okay, so let me show you how I'm going to get that. A is equal to the, let's go right here. I'm going to get the absolute value. That's the magnitude of the first residue. Call that A. I'm going to get the phase, which is the angle. That's the angle command of the first residue. I'm going to call that theta. I'm going to get the magnitude of the first pole. That's this pole. And I'm going to get the angle or the phase of that pole. So I need the four things: magnitude and phase of the residues and poles. And those are the ones I'm going to plug into that equation there that I showed you. Well, let me highlight those. I'm going to push the F9 key right now, and you can see that it shows up over here in the command window. And it gives you the magnitude, phase of the residue, magnitude, phase of the poles. And it turns out the magnitude of the pole is 1. All right. So I've written down those results here. There's the magnitude and phase of the residue, the magnitude and phase of the pole. All right, our final result is ready to be written down now. We're going to have a decaying exponent whose constant is 0.9 times 3, which is 2.7. Right, and then I'm also going to get 0.23. Remember, that was the magnitude of this pole from residue z, and I can add those together because they both correspond to 0.9, the pole 0.9, which I'm going to take 0.9 to the n, u of n. So that's from the initial condition, and that's just from the original difference equation. Okay, and if you remember the equation, we have to take the magnitude of the residue, it goes there, the magnitude of the pole, which is 1 raised to the n power, well, 1 to the n is just 1. The angle of the pole turns out to be the frequency of the cosine, and the angle of the residue is the phase value. So I've shown how they get copied into that thing. So that's the output of this system when there's a cosine input driving the system, and when there's an initial condition of 3. Okay, very interesting result. Let's plot it. I'm going to plot it from 0 out to 50, 0. And here I've just typed in, I haven't typed it in yet, I'll show you the MATLAB. I've typed in this difference, this final result here, difference equation. And the only thing I want to point out is whenever you have 0.9 to the n, see, I'm making a vector. N is equal to this vector, 0, comma 1, comma 2, comma dot dot dot, comma 50, right? So n is the variable in MATLAB. It'll have this entire vector in it. If I want to take 0.9 and raise it to a vector, MATLAB invokes some MATLAB theory, and you can't just raise a constant to a vector. What we want to do is we want to raise 0.9 to the 0, and 0.9 to the 1, and 0.9 to the 2, and we want to get a vector that has all of those element by element exponentials. And the way to do element by element is to precede this hat thing by a dot, and this means element by element computation. All right. Well, let me bring in the MATLAB command. So I've already typed this in. You see, n is 0 to 50. Everything's the same as we just talked about. I've got p angle. Now I'm just using the results here. I'm not using the I'm not typing in. See, p angle is 0.6266, and theta is minus 1.09. So there's the MATLAB command, and then I'm going to graph it using the stem command. N is the x-axis value, and y is the y-axis value. Let me highlight those, and I'm going to hit the F9 key, and you see it ran all those over in this window. And now I'm going to try to find it here on my, oh, there it is. And this is the result. Okay, this is you see what's happening is that we get a decaying exponent. It's not a decaying, it's a decaying result right at the first. There's some transient effects, and then this just turns into a regular cosine. Okay, so our initial condition results in some perturbation of the input or of the output right at the beginning, but then it dies out. So this is the steady state response, and we have a transient response that's added to the steady state response. Anyway, that's the end of this this example. Hopefully you'll kind of study this and be able to maybe do a MATLAB example, which may occur in one of the homework problems.